changing world. All right, thank you. Um, so I remember back in 2001, when I was still in college, um, I went for a movie which was called Artificial Intelligence, and this one was by Steven Spielberg. I'll be very honest, I really didn't enjoy it as much because I think I couldn't wrap my head around it, the whole concept. And for me, it seemed like something that would happen in the distant future. You know, it's not affecting us today. I didn't really understand it. But here in 2025, I'm here talking and introducing a masterclass on that very same topic. So clearly I was wrong, and clearly there's a lot to learn. So the series is led by distinguished faculty from US universities, and we're basically celebrating America's leadership and excellence in technology, research, and discovery. Beyond the science, of course, it's important for students to understand, what's machine learning and what the opportunities come with it. So these roles are going to be shaping industries and redefining skills. And what this really means for all of you is that it is an exciting time, but it's also a challenging time. And you are going to be doing jobs which do not exist today, right? So learning about these pathways today makes you future ready. And with that, I want to get started with our session today. I'm just going to quickly introduce Education USA for those of you who do not know us. Education USA is the official source on US higher education. We are basically supported by the US government, and our mission is to uh, send out information which is accurate, comprehensive, and current on anything that is to do with US higher education. We're a massive network. We're present in 170 plus countries. And in India, we have 4 centers, and we're headquartered here in Delhi. And my team today as well, there's Rupali, there's Parvinder. We're all joining in from the Delhi office. Okay. Um, you can stay connected with us. Okay. We'll be sending a link in the chat box as well, but you can also scan the QR code. We're, of course, social. You can also join us on social media. This will allow you to have regular updates from Education USA on all our amazing events. Okay, just a few housekeeping rules. To avoid any distractions, your camera and audio are muted by us. You can, of course, chat with us in the chat box. Please do post your questions. I'm sure Professor would love to answer our questions today, and we would love this to be an interactive session. Of course, because in the interest of time, I request all of you to keep your questions relevant to the session today. If there are other questions that you would like, answered, you can reach out to the Education USA team, and we are happy to do that for you outside of the session. Okay, we'll be leaving an email address and a phone number, and you can get in touch with us. In case you're not able to hear us, do check your audio at your end as well, and use headphones. But in case you're not able to hear us and there's a glitch, do let us know in the chat box. We will be posting some resources for you, and hopefully those will be really useful after you're done with the session. So we're going to be doing a knowledge session for about 30 minutes. And, and then we're going to be talking a little bit more about this particular field, the opportunities, pathways, the research, innovation, and then we're going to go into Q&A. So this is what the agenda looks like for today. And with that, I'm going to introduce our amazing expert for the first session of the Masterclass series. We have Professor Benjamin Carrion Schaefer from University of Texas, Dallas. And it is an early morning for him. And thank you, Professor, for joining us today. I am going to hand it over to you to take us through this amazing session. The screen sharing is still with me. Please do let me know when you want me to go to the next slide, and I'll be happy to assist with you. Thank you so much. Over to you, Professor.
You're muted, I think. Professor, you are muted. You need to unmute.
All right, thank you. Yes, you for unmuting me. So I'm really excited to be here. Thank you for the invitation. So a little bit about myself. So I joined UT Dallas 9 years ago as an assistant professor, and worked before at a different university in Asia and Hong Kong, then spent 5 years before that at the research lab in Japan working on electronic design automation before doing my PhD a long, long time ago. Next slide. This is my research team. That's why I'm talking about AI and hardware for AI. I had a research lab called Design Automation Reconfigurable Computing. You see there my graduate students. And a lot of the work that we do is on AI, but also on AI hardware. So I'm going to talk mainly on the AI software, but at the very end of the presentation, I also want to talk about the hardware because you might have heard about a company called NVIDIA. That's the most valuable company on the planet right now. And that's a hardware company. And the main reason why it is so valuable is because you can run AI models much more efficiently on these dedicated chips. Next slide. I'm also have the honor of serving as assistant dean for assistant dean for graduate student success here at the Johnson School at UT Dallas. And what this office is basically a dedicated office for our graduate students that basically we have activities for graduate students to make them successful. We have workshops for graduate students, and we have a dedicated career services. You see here, Lacey Henderson is the director of career services. So one of our jobs in the School of Engineering is to help you guys find jobs and internship, because we know that if you come to UT Dallas and you do a master's degrees in AI or computer engineering, computer science, bioengineering, and so on. If you do an internship, you have a high chance of converting that into a full-time job. So we try to make everything possible to help you get internships and then find a job afterwards. Next slide. All right, so let me start first with the very basics of how machines learn and what we try to accomplish. So the basic idea is that we want to have a complex nonlinear functions and learn that as a composition of single processing units. So think about our brain. We have a lot of neurons, but we can process very complex functions. And we do this through artificial neural networks, which is a collection of simple processing units like neurons, right, that are connected together in computers through wires, in our brain, obviously through in the brain. No? And the simplest neuron is called a perceptron, right? And I'm going to show you in the next slide, please, the equivalence between the brain and the computing in next slide, please. All right, so you see here, the biological neuron is what we have in our brain, where you have dendrites, your axon, your synapses, and so on, all connected together. And the equivalent in hardware is basically what you see on the right-hand side, where you have different inputs that are then multiplied with some weights, and they are connected, aggregated together to this linear combiner. And then the output of that X that you see there, is then passed through a nonlinear function. That could be, for example, a hard limiter, could be a threshold. There are many different types of functions. And the output of the function is this Y that we want to achieve. So think about this is a single neuron. And the main idea is that you have different inputs that could be, for example, you want to know, you look at a piece of food and you have different inputs to the computer. For example, the image, you have the sound, you have the smell of the food. Now, based on the different inputs, you want to assign different weights to determine if you're going to like the food or not, right? And for example, maybe the smell has a higher weight. That's why you have to multiply the smell by the larger weight. Maybe the hearing sound, the sizzling of the food is not so important, so that weight will be lower. Right? And then the visual appeal, of course, is important, so that other input will have a higher weight. So all the inputs that you have, you multiply by specific weights, you add them together, you combine them, and that's the output of the neuron. And then you have this nonlinear, what's called activation function to give you the output. Do I like the food that I'm seeing and I'm hearing, or do I not like the food? So that is the basics, right? The basic element in a computer to learn are these neurons, and the key is how to find those weights. Next slide. So the basic architecture of the basic component is, as I mentioned, is this neuron, this perceptron that have as many inputs as needed by your machine learning model, but based on what you want to learn. The weights, right, the importance of the different inputs that are all add up together. Then you also might add a bias, which is a constant, just adding a constant, and then pass the output of the neuron to this activation function. And that's the basic components of how computers learn. Now, complex artificial neural networks have thousands, millions of trillions of these components. And you can already see the difficult thing is how to find the right weight combinations such that whenever you have a large number of inputs, you get the desired output. Right? Next slide. So a very simple example is this here. Imagine you have this table, this truth table, where you have three inputs, x1, x2, x3, and you want to create a function, what you denoted here as a black box, that can actually replicate the output, can generate the output y exactly, right? Based on what on the training data that we're seeing here with the different input combinations and the expected output. So one way to do that through what I just showed you with the neural network is, next slide, is create a neuron. And you see here, we have three inputs. We train, and I'm going to talk about how to do the training. And we find that each of the input has the same weight. And the weight is 0.3, 0.3, and 0.3. And then we have a bias, 0.4. And then we have a step function as this nonlinear function. So that is our neural network, and we've trained it by finding the weights in this bias. And let's see with an example if this actually works well. For example, let's look at the first entry where you have x1 is 1, 0, 0, and the output should be -1. If you take x1 is 1, you multiply it by 0.3, the output is 0.3. The other two inputs, because they are 0 times 0.3 is 0, so 0.3 plus we have the bias, we subtract it, minus 0.4 is minus 0.1. Then you pass it to this step function here, and because it's a negative value, it's smaller than 1, the output is -1. So you see the output is correct. So now, if you try all the possible values in the table, you will see that it always generates the correct y. So we've trained a very simple neuron to actually create that function that I just showed you there. Right? Next slide. Now, as I mentioned, neuron, this is a very simple, the basic component, but you might have heard the term deep neural networks. And deep neural networks are networks that have hundreds, if not thousands or millions of these neurons. And they became popular about 15 years ago because it was shown that it can lead to really good results, for example, for object detection, classification, recognition, text, data tracking, speech recognitions, and so on. All right? Next slide. And these neural networks, they have three main components. The first one is what you see at the very bottom, the input layer. You have as many inputs as required by the function that you want to achieve. For example, if it's an image, maybe every single pixel is an input. Then you have what's called the hidden layers. These are the layers that basically will start getting the information and extracting the information from the image. And at the end, you have what's called the output layer. And you have as many neurons as outputs you require, right? For example, if you only want to detect is it image is a bird or is it not a bird, then you only have one output. But if you want to detect is the image a bird, is it a phone, is it a computer, you need three outputs, right? The output that tells you what is the probability that an image is that, right? So an important thing to know that in this deep neural networks, you have input layers, multiple hidden layers with a certain number of neurons, and then the output layer. Next slide. A very simple example that's often very used, and I use it when I teach, is the handwritten number detection. Here you see in this figure that you have an image with a number. And for us humans, it's very easy. It's a 3, but for computers, not that easy to understand that is a 3. So the way that we can create a neural network that basically creates as an input layer as many neurons as pixels. So every pixel is extracted into that input layer. And then we have different number of hidden layers with different number of neurons. And that's where the designer has to come up with the architecture telling how many neurons, how many hidden layers you have. And then in this case, the output layer, you have 10 neurons as output layers because we have 10 different digits that we can have from 0 to 9. And the output of this neural network, once it's trained, will give you the probability that that image is actually a 0 or a 1 or a 2 or 3, 4 until 9. So in this case, 3 should be the highest number, highest probability of being a 3. Next slide. So then this is the input layer. We see this is the image. In this case, is 28 by 28 pixels. We have 784 pixels. So that means we have 784 input neurons. That's the input layer. Every single pixel is then passed to one of these inputs to our neural network. Next slide. Then these neurons, as I mentioned when we looked into the single perceptron, we train create the different weights, are all multiplied by the different weights and then added together, accumulated. So that is the output of the first stage, right? And all the neurons are connected together. They're all connected together. And the weights is basically the strength of the individual connections, right? Next slide. And then we have the output layer. And the output layer, in this case, we have 10 outputs that represent the probability that this image that the neural network has analyzed is a 0, is a 1, or is a 9, right? So in this case, we have 10 output neurons, 10 neurons. Next slide. And then the hidden layers. This is probably the most important part. And the hidden layers, you as a designer have to come up with the architecture, have to determine how many hidden layers do I need? How many neurons per hidden layer? In this case, in this example, there are 2 hidden layers with 60 neurons each. And that means because all the neurons are connected together, that you have in total 784 input neurons times 16 neurons plus 16 times 16 plus 16 times 10 weights, because you have all the different neurons plus the biases. That means that in total, that neural network has 13,002, about 13,000 parameters, weights and biases that need to be found. They need to be fine-tuned such that this neural network works correctly, is accurate. When I said correctly, works accurate, it means that when you see a specific image with a handwritten digit, and it's trained based on a data set of handwritten digit, the output can accurately predict, is it a 2 or 3 or whatever number it is. So you can already see the complexity. This is a very simple neural network, and it has to be trained so that the 13,000 parameters, weights, and biases are set up correctly, right? And that's the hard part of these neural networks. And the good thing is a very structured approach. The architecture is very clear from the hardware side, but then the problem is how to find those weights and biases, right? Next slide. So then how do we find those weights and biases? You have to train and test it. So what you typically do is you have a data set that you already know the output, expected output. So in this case, you have thousands of images with numbers and you know the expected output. And then you train the neural network such that you get the weights and biases. You start randomly and you fine tune the weights and biases. Once you get a set of weights and biases, you test it with an unseen set of images. You cannot test it on the training data. You have to train it on a new set of images. And then you see what is the accuracy of the neural network. If the accuracy is still low, you go back and change some of the weights again. You then test again with the new test data. And then if it's not accurate, you modify the weights again. And this is done, next slide, through what is called back propagation. So then first you take the training data, you know that you have the images and you know the expected output. In this case, should be a 3 and the expected output should be a 3. So you can randomly set all the weights first. And then if those random weights most likely will not lead to the expected result, you have to go back, and mathematically you can do what's called back propagation, right? And you set some of the weights and you move it slightly either up or either down. And then you try it again and you see if that has improved anything. You calculate the cost function. If it's not good enough, you back propagate again, modifying some of the weights and biases, and you test again. You go back and forward multiple iterations until you find a set of weights that actually work for that particular application and for that training data. That's why the training data is so important. Next slide. Now, you might have also heard about other types of neural networks called convolutional neural networks. And these are a class of deep neural network composed of specifically suited for visual analysis. Like for example, in this example, you have a picture and you want to detect, you want to predict, is this a bird? Is it a sunset? Is it a dog? Is it a cat? What kind of animal is it, or what is it? In this case, the architecture is slightly different, because if you look at the figure, at the very end, you have what's called the fully connected layers. That is what I just mentioned in the previous slide, where you have the input layers, the hidden layers, and the output layers. But for these particular image processing up neural networks, you need some initial stages that do what's called a convolution and a max pooling, and you can loop through that. Basically, you have to multiply some pixels together, you group them together, and you pre-process this multiple times before you can pass it to the actual neural network that I just mentioned. Right? Next slide. And you might have heard about these were one of the first applications that really exploded and made neural networks very popular. You might have heard about neural networks called LevNet, AlexNet, VGG, ResNet, and so on. And you can see on the figure the different architectures of this convolutional neural networks. For example, in the earliest one of the earliest convolutional neural networks, CNNs, the LeNet 5, you had first a convolutional layer, a pooling layer, and then convolution, pooling, and then you have three fully connected layers. Fully connected layers is what we saw before with the handwritten number characterization. And you see AlexNet was more complicated, and then the ResNet more complicated, right? And you have many more layers. But all of these layers, they are based on setting a set of weights and biases that can be learned, even the convolutional and the pooling layers, right? So that is the key thing. All right, and they've shown that these lead to very, very good results to identify elements in images. Right. Next slide. Now, the hottest topic that you probably can imagine right now is large language models. This is the hottest thing. Everybody's using large language models for anything, and the key is that the original large language models, that what they try to do is predicting just the next word from what you type in. For example, if you say the boy went to the, and then the large language model has been trained and it gives you the probability of what the next word should be. So cafe, hospital, playground, and so on. So then by computing word by word, right, it actually can create phrases that make sense, right? And that's the main thing with large language models. The main problem of these large language models, right, is that they have billions of these parameters. Remember, I told you that in the handwritten number generation, you have 13,000. Now, for the Meta Llama 3 model, has 70 billion of these parameters. And it is estimated in the OpenGIS ChatGPT has around 1.8 trillion parameters. Think about it. 1.8 trillion of these weights and biases, they have to be set accurately such that the model works correctly. And that's a huge challenge. Huge challenge because it takes months to train on dedicated computers and farm of servers, right? And you have dedicated chips like GPUs to do the training. And then once you have the training and you found the 1.8 trillion parameters, you have to run these models that are so large on dedicated computers that are based right now on GPUs. And that's why NVIDIA is so valuable these days, because these large language models can only, the very large ones can only be run on these GPUs, right? Next slide. Now, I also want to talk a little bit about the hardware side, because what everybody's seeing these days is the software, the models, right? The large language models, the convolutional neural networks, and so on. But there's a lot of things happening on the hardware side, and that's an area where I actively work in my research. So, for example, you might have heard about these field programmable gate arrays, FPGAs, and there's a family of dedicated FPGAs called, for example, from AMD, the Versal FPGAs, that basically have embedded processors, have embedded a reconfigurable fabric, and have dedicated neural processing engines, similar to what Apple has in their A17 phones and so on. So you see here in this slide, these are the FPGAs. You have a scalar engine is your processor. Your adaptive engine is where you map the AI engine, and then the intelligent engine here is actually where you map other type of hardware accelerators and so on. So if you click now again, next animation, you should see the architecture. Next slide, or click one more time here. You see here, that is the architecture, right? And that is the architecture. And these are all in one single chip. That's the interesting thing. Transistors are getting smaller, and you can build extremely complicated chips where you can map the processor running the operating system, different types of AI engine, DSP engine, and then these adaptable engines where you can run and train those neural networks, right? So a lot of things happening on the hardware side as well, right? In the computer engineering, hardware design, right? Next slide. Right. So now this is a very basic. No? So then, what if you want to become an expert in AI and you really want to learn about the software, the models, how to do efficient training, how to find the weights efficiently, how to create the architecture, or maybe you say, I want to work on the hardware side. I want to build architectures that will run and train these models quicker. So one of the advice that I give the students is that it's important to think about graduate school. And the main reason, the way that I express it is the following. Imagine that the circle that you see here is the human knowledge when I was at your age, when I did my undergraduate, maybe my PhD 20 years ago, 20 years ago. What you see inside the Internet Explorer, the Nokia phone, and so on was the best and the greatest technologies at that time, right? But look what have happened in only 25 years. Look what has happened. All these new technologies, right? You see the human knowledge right now, 24, 25. We have ChatGPT, self-driving cars, systems on chip, robotics, data centers, 5G, renewable energy, smartphones. That did not exist when I was there. So you can see the human knowledge, that circle has expanded, right? We have much more information that need to be also learned. And if you click on the next animation, the main problem is your undergraduate is still 4 years. That has not changed. At least in the US, it's 4 years. It has not changed. And think about it. Your undergraduate is 4 years. Out of those 4 years, probably the first 1 or 2 years are basic stuff that you have to learn, like your math, linear algebra, basic knowledge. So you only specialize in the last 2 years. So we don't have time to teach you these advanced topics when you're an undergraduate student. That's why I recommend you to think about graduate school to learn about these specific topics. Right? Next slide. Now, why the US? If you look at everything that is happening in AI these days, you might have heard about something called ChatGPT. Most likely, you guys are using it maybe for your assignments and your homeworks as well, because it works really, really well. That brings some other challenges for us as educators. But ChatGPT, Gemini, Meta AI, Copilot, Grok is the latest from Elon Musk. All these large language models, they all come from the US, right? And these are companies actively putting billions of dollars in investing in these large language models, and that means job opportunities. Now, apart from these large language models, what I included here is a textbook here of companies that try to build large language models into the products. So there's a boom going on now, which is equivalent. I remember it reminds me to what happens when the smartphone came out with all the apps and all the app stores and the different applications, and before that the internet with all the internet web pages and portals. And there's a boom in companies leveraging LLMs for different things. How to make you more productive for writing documents, for doing your taxes, for image processing, and so on. Right? So there's a lot of opportunities in the US to either work on these large language models, but also how to leverage in different domains. And that's what I call software AI. Now, on the other side, there's also a lot of work on hardware AI. We have NVIDIA, as I mentioned, this is the largest, most valuable company in the world because their GPUs are specifically created to run and to be able to train these large language models. But not only NVIDIA, we have AMD working on these type of chips that specialize to run LLMs. We have Google building the tensor processing units. With Amazon now, with building their own chips. So there are many companies, of course you have Apple as well, building their own hardware that runs these large models efficiently. So if you're interested in hardware, it's a great place to be as well, right? A lot of companies wanting to build their own hardware and tightly integrate the software stack with the hardware stack, right? So then AI models, leveraging those in different applications, and then the hardware AI as well, right? Next slide. Now, I have a few more slides for you, like why UT Dallas, and let me introduce you to our university. So then the three gentlemen that you see here and their wives are basically with the founders of Texas Instrument. Well, Texas Instrument is right across the street from where in UT Dallas. And they actually they founded UT Dallas in 1961. So they wanted to create a better higher education opportunity in North Texas. And they did establish, right, the Graduate Research Center for the Southwest, and that later they donated everything, the land and all the facilities, to the UT system, University of Texas system, and that's how UT Dallas came. Right, next slide. This is the picture of when they founded UT Dallas. There was all there was. There was one building, and that was the first building that is still standing these days. That's called the Founders Building, and that was UT Dallas a long time ago. Next slide. And look at this. This is UT Dallas right now, a vibrant university where we do the state-of-the-art research. It's a very engineering-centric because TI founded us. So we put a lot of emphasis on engineering. The largest graduate programs are in engineering, the largest PhD production. We have 6 departments. And I think it's a great place also, not only the university, but North Texas. It's growing fast. Many people moving from California because taxes are lower. So many companies are relocating. And if companies relocate, means more job opportunities as well for you. Next slide. Now, if you want to work in this area of AI, and again, I mentioned I divided in software AI and hardware AI. We have 6 departments in the School of Engineering: bioengineering, computer science, electrical and computer engineering, material science, mechanical and systems engineering. If you want to work on the software side, on the large language models, on the neural networks, the architecture, the training, the software side of that, computer science is a great option for you guys. They do a lot of great work with professors doing research, specializing on that particular topic. Now, if you like this hardware side, if you like the architecture side, building the chips to run the hardware, the AI models faster and do the training model, then electrical and computer engineering will be a good option because we have many colleagues building for other devices. They are specialized, right, to build these perceptrons, the neurons, to actually people like me that build the architecture or even the tools to actually synthesize and create optimized hardware architecture. They are the low power or high performance or a mixture between all these. No? And then all the other departments, especially maybe bioengineering or even CS and ECA, we have many colleagues that leverage either the software and the hardware or both to actually for different applications. For example, in bioengineering, many of our colleagues, they use AI to help medical doctors, for example, find cancer. Sometimes they do an X-ray and it's hard to see if there's a cancer or not. That's where large language model, if you have neural networks can be very useful. If you have a large training body of these images, X-rays, and the doctor knows, oh, this led to cancer or not, you can train these neural networks to either see a new X-ray and tell you if there's cancer or not. Right? And these models are now even more accurate than doctors, right? So there's a lot of work in bioengineering, how to apply these neural networks for different domains, like in bioengineering and so on. Next slide. Now, the last slide that I had for you. So what are we looking for? So we're looking for students that are really passionate about engineering, right? But we're founded by Texas Instrument, and we're called a nerd engineering centric school. So we don't have a large sports program. I think we are the strongest, one of the strongest universities in the country in esports. Remember, esports is now a sport. Think about it, right? So then we're engineering focused, centric, passionate about science and engineering. Engineering is in our DNA. So what we want is students that are also passionate about engineering and computer science, that are hardworking, independent, that are curious, that you're able to teach yourself and learn about, they're passionate about these new technologies. And one of the differences that I've also noticed teaching in different countries is here in the US, we expect active participation in class. We want you to ask to question us in class when you're teaching. We want you to participate in student organization. We do facilitate that as well. We have many student orgs, right, that we want you to participate, and so that you don't just take courses at UTD, that you also participate and become a comet is our mascot, that you become a comet here at UTD. And that's all I had for you. Next slide. Any questions or anything that I could answer?
Right. Thank you so much for that knowledge session, Professor. I think I got some of that, but I think there's going to be a little bit more reading that I need to do. But thank you so much for that. I think we have some questions in the chat box. Should I relay those to you? I'll read them out to you.
Yeah, okay. Please.
Yeah. All right. So we have a question from Kshitij. Professor, I'm an aspiring technical professional. I have some projects and some work experience as a software engineer in my CV, in my resume. I want to do projects that land relevance for most JDs out there, job descriptions. Do you have a tip for me? I initially thought about putting in some agents centric projects that focus on some specialized use cases.
So right now, the key is there's a lot of discussion about that large language model will completely substitute, and they're doing it now, entry level programmers. So if you have no experience in programming, it's a you're in a tough spot right now. So what I would recommend people, especially from CS, is that you have to learn how to leverage large language model to be more productive. Right? You have to start using large language model to be more productive and use, as you mentioned, agents to be much more productive. So when you go to a job interview saying, hey, I don't want you to take my job. I want to take some other people's jobs because I can use large language model. And maybe if you hire me, I can do the job of 2 or 3 programmers right now. So you want to be that person that can leverage large language models and you can make use of that.
All right. Professor, we have one question. I think this comes from when we've interacted with so many students as advisors. What is the one unsolved problem in machine learning that you think a master's or a PhD student should tackle right now? What are some of those burning sort of areas?
So there are many, many areas. This is the hottest topic. And for example, in my area, in my particular area of hardware design, we are leveraging large language models to build hardware chips. How to automatically create hardware chips. So for example, output Verilog or VHDL and create a computer architecture. The problem is there's not enough training data for that particular field. There's a lot of training data out there for C programs or Python programs that the large language models, the training part can actually learn from. But the training data is a big problem. Other problems are power consumption. Data centers now, they're expected to require like nuclear power plants. How to reduce the power consumption to run these large language models and do the training. How to reduce the training cycle. It takes months now to train large language models. So they're getting very large. The architecture of the large language models, now they're really large, but can you create more smaller, specific large language models for specific things, right? Fine-tuning these large language models. So there's a lot of work that can be done in large language models, in AI. Yeah.
All right. Thank you, Professor. We have some really good questions coming in, and I'm glad we have some time. This is a question that we all talk about. Which jobs, as per you, are most likely to disappear because of AI?
So right now, the main discussion right now is level entry programming jobs, basic program. If you just graduate from CS and you have not a lot of experience in programming, AI can do very good job programming. So these are the big discussions right now that maybe companies might not need this level entry programming jobs.
Right. All right. So 1 second. One other question is agentic AI or Gen AI, which has more potential jobs?
Both of them. Agentic AI is basically an AI that it can solve the problem. You ask him to do something, it gets you the answer, and then it actually proposes and solves the issue. So there's a lot of agentic AI now in hardware design, for example, in software design, because they are large language model that can actually feed back and then you can solve the issue. So they're very useful for design, for programming, and so on. And Gen AI to produce things, for creating contents, for doing so. These are both very important applications of AI right now. These are at the top, both of them. I won't be able to choose one. It's like choosing between your mother and your father.
Right. All right. What advice will you give to young students, Professor? A student in grade 9 or a student who's just entered college right now, who wants to get into this field. What advice do you have for them? How do they actually sort of choose where they should be, focusing their efforts in?
Yeah, so remember what I said in the slide. In AI, there are 2 areas. Maybe it's the software and the hardware side. First, what are you interested in? Are you more interested in the hardware side, in building the chips for AI, or are you more interested in actually the modeling, the software? The software side is the easiest one because you can be very productive very quickly, and you just need a compiler, you just need an online environment, and you can create your own neural networks, you can train them, you can apply large language model for different application domains. Hardware side is harder because building a chip or prototyping is more expensive and so on. No? So first, based on your passion, but then get involved and learn the theory behind it. Don't be just a user. Especially if you're a college student, you should be able to understand the theoretical foundation of these models, how they operate, how they are trained, and so on. I give you a very high level view, but you should understand the basics, everything inside. That's the difference between someone who might not go to college and maybe just learns it from the internet to someone who actually formally gets a degree and learns about these things.
Right, Professor, I was watching a podcast recently, and Elon Musk, in fact, was talking about the fact that there are a lot of companies now hiring people without college degrees, and they're more skill-based sort of applications coming in. So, in case, there's of course, we have a strong point for education, higher education at an institution. But what are the good resources for learning AI? If someone like me, a layman, I come from the field of psychology and education, I want to learn something in AI. What are some of the good resources out there?
So when you Google AI and large language model YouTube videos, there's tons of videos out there. There's a lot of web pages where you can have tutorials and so on. So now there's a lot of online courses, certificates. There's even companies like Microsoft, and they have certificate. They want to train people to have people have those skills that they need then to be hired. So there's a lot of certificates that the companies now issue, and they have their own training programs that specifically target those skills that they think they are relevant to them.
All right, great. Thank you so much, Professor. So Tanushree says, thank you for the valuable information, Professor Schaefer. I represent an educational institution, which is based here in India, and we are very interested in application research in AI ML. We have 2 campuses with undergraduate courses specializing in AI ML and data science, over 100 students. So if there's any way to discuss research or specific program related collaboration,
Sure.
Yeah, if you have something to say
Send
to
me an
that,
email.
but I can provide more information as well. Yes.
Yeah, or send me an email after this, and I'm happy to put you in contact and share more information. But do drop me an email. You have the email in the screen, so if you want to take a picture and then email me later, and I'm happy to
All right.
contact you.
Thank you. And Tanushree, we can also share some information for you from the education perspective. And Rupali, I encourage you to share, get Tanushree's number or email address, and we can share that with her. We have a question from a student who's an undergraduate student here in India in AI ML. I have a very strong desire to become an AI ML engineer. I need a word of advice from you to become one. So what are some of the key points of advice that you can give to students who are looking to get ahead in this area?
So there are many degree programs that the university sometimes they react very slowly to these changes because you still have to get the foundational courses. You need to have a strong math background and so on. So you need to put a lot of effort on your side as well to keep up with the new trends and to be a lifelong and self-learner, teach yourself these things. Because remember what I told you, your undergrad degree is only 4 years. And it's not very flexible because you still have to learn the basics. So one thing that you really have to do is put effort on your side and be a self-learner and a lifelong learner because this moves very fast. So that consider going to graduate school and learn by yourself because most likely in the university, we touch AI in some courses, but we don't have the time in 4 years to give you the latest and greatest in the latest technology in AI.
Right. That's a big challenge, Professor. There is another question. I'm going to try and get as many questions as possible. Audience, just hang in there. Hello, Professor. Thank you for the session. I'm currently a high school student working in AI and machine learning. I've conducted independent research and have a few peer-reviewed publications in areas like deep learning and multimodal AI. I'm planning to apply for undergraduate programs in the US, including your university, UT Dallas. From your perspective, what would be the most important next steps for someone like me to strengthen their application and research profile before entering university?
Well, if you've done already research and you've done some publication of the papers, well, that's the only thing that maybe might make it even stronger is you have some open source releases. You've done something that you can then publish and make it open source so people can start using it, and you can show your GitHub repository and you can show that people are downloading it and using these things. That would be even better, no? If you can do that, for example.
Right. Professor, we're getting some similar questions about, I think, people wanting to enter this field. For example, there's a student who has a computer science background and they are a software engineer and they do have experience in systems and ML. Now they want to explore the hardware side through a PhD program and do research. Are there any specific prerequisites or preparation for someone coming from a CS background, getting into hardware side of AI, ML at the grad school at a PhD level?
Yeah, so think a PhD is a very different, unique program. PhD programs, the good and the bad thing of the PhD program is it's free. PhD is free. Students don't need to pay for a PhD. Undergraduates and master's degree, you're receiving education, you pay for it. A PhD is free. We, for example, PhD students, we pay a stipend of $2,150 plus health insurance and tuition. It's free. But there's nothing free in life. When I said free, is who pays for that? And the money basically comes from the professors. Part of our job that many students don't see is I'm writing grant proposal all the time. I show you an overview of my PhD students. I support them through external grants. I have to write grant proposal with ideas about how to create computer architecture and all these things, and I get the money. With that money is when I hire students. So what you have to do is talk to professors who you think you could work with, and then you'd have to do an interview with the professor and then see if the professor has funding and is interest and you have the right background for the professor to hire you. Now, if you want to switch careers from CS to maybe computer hardware design, if you don't have that right background, maybe a professor might not want to hire you, and because I would have to sponsor your PhD for 4 or 5 years. Right? So we are very careful who we hire because unfortunately we don't have so much money. But the idea is that you talk to many professors and then interview with them, and then basically you have to convince them for them to hire you as a PhD candidate. The professor, don't apply first to the university. The professor is the one who has the funding to hire you as a PhD student.
Right. That's really, very, very useful information, Professor. Professor, I think you did touch upon this, but there's a question for the topic. What is the basic difference between ANN and CNN? And I know that's not the news channel. So could you tell us a little
Artificial
about
neural network is what I just showed you. It was called a shallow, small neural network with a certain number of maybe inputs and maybe one hidden layer, one output layer. Deep neural network is DNN is we have multiple of these hidden layers. You have many more neurons. And CNN, convolutional neural network, is basically neural network specific for image processing.
Right. And Professor, I have a question. It's how are U.S. universities, with all the resources that you have, how are you meeting the demands of the industry? So, for example, you have companies, they require certain kind of skill set. What resources, what opportunities would a U.S. university have to kind of meet that demand for industry?
Yeah. So first, what we're changing the curriculum, is even at the undergraduate level, to include machine learning courses. So first, a dedicated course about machine learning and applied machine learning. So these are typically elective courses the student can take if they want to specialize in that field. Also, we're building machine learning into each of the courses. For example, I teach a computer architecture course, and I ask students in my homework, I've redone all the homeworks, and I ask students to use ChatGPT, to use AI, because it's going to be there. Like when I was doing my undergraduate, the internet came, and then everybody will start using Google. And some professors were scared, oh, Google will break everything and people will not learn anything because they will Google everything. But Google has been there for many years, has been very useful, and we use it. And the same for large language models. So now ChatGPT is here, and we need to leverage it also for teaching and for students to do maybe more complex projects. Instead of doing a simpler project now, I ask students to do larger project, and I ask them to leverage also ChatGPT, large language model, to create more complex and interesting projects in classes.
Right. Professor, one question, and I'm picking up a few from the chat. If a student is applying to a graduate school at your university, and a requirement is, of course, this an essay that they would require to write, like a statement of purpose, what really should be the focus of the SOP, particularly for this particular area, at your university?
Remember what I told you. We want people who are passionate about engineering, about science, about learning about these things. So show us your passion. That's important. That you really want to learn this. That's important.
Right. Okay, Professor, what is the difference between NVIDIA chips used by ChatGPT and Chinese AI chips used by DeepSeek?
So the architecture is different. And not only the architecture, the software, and the key is the software. NVIDIA was very smart. 25 years ago, they created something called CUDA. CUDA is a programming language. They're allowed to program GPUs. The basic architecture of these AI chips are GPUs. But NVIDIA already identified 25 years ago that you can actually reprogram these GPUs to not only do image processing applications, but for other general purposes. That was what's called GPUs, general purpose GPUs. And they created a programming language called CUDA to actually allow you to program these GPUs for any other application. for high frequency trading, for scientific application, and so on. And that is what's happening. It's first the architecture, the interface, how the data comes in and out of the chip, and how to program these chips is very important.
Right. I think we have time for one last question. Students in the audience, thank you so much. Really good questions coming in. Okay. What are the key deciding factors for a successful? Okay, I think we've already covered that. Let me just go on to another one. 1 second. I'm a working professional in the ICT domain, always passionate and keen learner in AI, ML, and STEM fields, looking for emerging technologies to engage in current times. Could you guide us a little bit on that? What are some of the emerging technologies that students should be, well versed with?
So, of course, large language models, but you need to understand how do they work. The underlying architecture is important. The model, how does it actually work? How to train them, how to fine tune them for specific area. Now, and it's important with large language models, the generic ones from ChatGPT are very, very large. But remember what I told you, trillions of parameters. Now, one of the key things is, can you create a much, much smaller large language model fine tuned for a specific application? Also, many companies, they don't want to use the cloud because cloud is, where is the cloud? Is it maybe in the US is very scared of China right now? The cloud might be in China. Someone can steal the data, the training data. So can you actually build dedicated models that can be trained locally so you don't have to share the data, right? Data is very important these days. So that all these things about large language model, the training, the fine tuning of large neural network, and then applying it to a specific domain, that makes a big difference. That can basically, you can have an entire career based on that.
Okay. Professor, I'm going to leave you with one last question, and this is from Dr. Nafis. Does University of Texas Dallas provide data set repositories to access, basically access to those repositories for outside researchers that are not part of UTD?
Yeah, that depends on the professors. Every professor has its own research lab, and every research lab is almost treated like a technology startup company. So every professor might have its own data set. And then the idea is that you might have to reach out to that particular professor and then maybe agree on sharing the data set or not.
Right. All right. I think with that, we're getting some questions which we've already answered previously. So I think with that, we can end this particular session. Professor, thank you so much for being here today. We've gotten really good feedback in the chat as well. Audience, if we have missed answering your questions, you can always write into us at indiaeducationusa.org. Any faculty members, researchers in the group who want to get more information about collaborations with UTD, please do write into the to Professor Schaefer right there with his email address. Or you can also reach out to Education USA, and we will be helping you with information on partnerships. Thank you so much, everyone. Have a great evening. Professor, have a very good day. I know it's an early start for you. Thanks a ton for doing this for us. Thank you so much.
My pleasure. Thank you, everyone, for joining.
Yeah. Bye-bye. Take care.